So Marcel will present an introduction to the landscape theory and localization. And
so do you see it?
Yes,
here?
we see it. Perfect. So Marcel is from the Polytechnic.
Okay. If I switch like this, do you see it in a mode presentation, in a different mode?
Smaller. If you would, if it was, yeah, this is full screen.
Okay.
This is probably better full screen if you don't mind.
Okay, sure. I will keep it that way.
Okay, so I think we can start. We'll have a longer break afterwards, I think. Thanks.
Okay. Thanks a lot, Thomas. First, so is it okay? Do you hear me?
Perfect.
Okay. So first thing, I could thank the organizer for inviting me, but okay, that would be unfair. First thing, this is a school. This is not a workshop. This is not a international conference. So this is a school. This means that we have to be interrupted while we talk. We can have questions. I'm not playing a concerto. So yes, please, if maybe things are new here for some of you or for many of you. So please don't be afraid to ask questions, especially students, because this is aimed at students also, or maybe mainly. Second thing, I'm going to talk about landscape theory localization. This will be a talk that will be not my work only, it's the work of many people in mathematics, in theoretical physics, in cold atoms, who are listed here. For some of them, there might be a very strong feeling of déjà vu in my talk. So, but that's going to be normal. I'm going to go back from the beginning. This all takes place within the framework of Simon's collaboration on localization of wave that started 2 years ago, but which is a strong collaboration between mathematicians and physicists. But it's also a work that has begun about more than 10 years ago, together with Svetlana. So the 2020 has been a year especially rough, and also for the physics community, because the main guy that we are talking about in all this school passed away at the beginning of the year in March 29. So I just wanted to say this, to pay respect to him for his tremendous work. And also I wanted to take this opportunity to pay my respect to another person who was a seminal in the study of localization of wave in our lab, and studied especially localization near rough boundaries. It was seminal in introducing the geometry, the fractal geometry in some part of physics. This is Bernard Sapoval, and together with him, we designed a noise abatement wall where we used localization of this time of acoustic wall, not of quantum waves, of acoustic waves, not quantum waves, to design a wall of world record performance. Okay, so he passed away about a month ago. So I wanted to pay my respect to him. So the talk that I'm going to present today is almost orthogonal to the one of Dominique, and I think it's a good thing. Orthogonal in many ways. First, most of the approaches to Anderson localization so far have been since it has been discovered by Anderson. The essential of the work has been based on the fact that we are dealing with random object, with random potential, with disorder, and trying to model the disorder. And for that, the approaches in physics have been mostly statistical, and the tools that have been used for that, the theoretical tools, have been based strongly on probabilities and on statistics. So I won't repeat the Dominique's talk. This is like a sketch. My talk will be also orthogonal in the way that most of the language that Dominique used to present and to introduce you to Anderson localization was in, as you can see here, was sort of propagative, in the propagative language. So that the waves, they were understood like scattering in a disorder medium, diffusing, or being localized like this, with a critical exponent at the transition. I will present something that will be mostly in the modal language. And so it will be not at all statistical, you know, it's not at all in the work of the statistical. Not to say that it's not opposite. That's why I said perpendicular, it's not opposite. So the statistical and probabilistic approaches have been tremendously effective to give you know, many results. The thing is that what we are aiming at with the landscape theory is to say maybe there is something at work here behind wave localization in random or disordered media. There is something that is even more general. There is a machinery that applies to all wave equations and a machinery to confine waves. And maybe that in the particular case of random media with IID disorder, you have some additional property that come into play. But maybe there is also a deterministic machinery to dig up somewhere. So in the statistical approach that have been presented, so disorders is also always described with statistical properties. There is lots of numerics involved, and we are lacking deeply analytical expression, if they are possible. As Dominique mentioned, we are still looking for an exact determination of the value of the mobility age, and the situation may be even worse where correlations or interactions come into play. So this is something that we are trying to complement the picture of the statistical approach, not to destroy them or to contradict them. Sorry. So starting from the beginning, the localization landscape theory. This is we will be in the framework of quantum waves. So we will use Hamiltonian, and we're going to assume that the Hamiltonian has a potential part which is positive, or at least that the Hamiltonian has a positive spectrum. And if it has not, then you simply shift it up, so that so we need the only thing that we request so far is that we have something that is at least bounded from below in spectrum. So this is as I said, I'm going to be in the modal framework. So I'm going to look at the time-independent Schrödinger equation. And so the paradigm is that posed by Anderson was that if you take a random potential V, here we are in 2D, like 20 by 20 chessboard with a uniform random potential. And you compute actually the 5 first quantum states in this random potential, then you get something that looks very much like the exponential localization predicted by Anderson. The localization landscape that we're going to introduce is an object, a mathematical object, that solves an equation which is not an eigenvalue equation, that the whole story is to say, and this is maybe the first take-home message, a lot of information about the eigenvalue problem and in terms of spatial information and spectral information are contained in this object. There is a lot to extract from this quantity, which is much easier, of course, to compute. Solving this quantity, for example, in this case, you get this field which looks like a field of positive bumps. It's a positive function. And here are the quantum state plus superimposed with the valley of this object, this u of x, this quantity, which is here 2D function represented in 3D. And the valley of, so if you look at the bumps here and you look at the regions where the landscape is small, which are called here the valleys, and here you see a pattern which is interesting, is that the valley, they seem to go around the localization and to sort of detect the regions where are going to appear these peaks. So the whole story is here. So very often, the first question that comes to mind, or that comes when we present the landscape, is why did you think of HU equals 1? The first incentive for thinking to HU equals 1 comes from this very simple derivation. If you have an equation, a quantum state psi that solves the time-independent Schrödinger equation, then you can invert this relation by invoking the Green's function, the zero energy Green's function, zero frequency Green's function of this operator. You invert this, and then you take the absolute value of psi, and this E comes out because it's positive. Here you take the absolute value of that, and this quantity comes out because you take the supremum of psi, and you get, at the end, what's left is this, and you call this U of x. So in short, if you take this equation, you divide by the supremum, it means that at any point of the domain, the absolute amplitude of psi normalized L infinity is smaller than E times U. And moreover, since G is the Green function of the second order operator, it's positive. So you can remove this absolute value here, you get that. And this, by definition, is the solution to HU equals 1. That's how HU equals 1 came into play. And actually, so what does the equation say, which is simply a linear derivation, tells you that when U is small, then you expect psi to be small, at least in amplitude. And so what it means is that you take this U function, you look it from above, you look at the valley, so you draw the valley, here they are. And so they are, the deep valley are traced in darker. And you look at this valley, and that are these red lines that are plotted here. So do they really detect the localization regions? You know, these regions where U seems to constrain the amplitude to be small. You take the first 5 eigenfunction, you take the network of valley, and you superimpose these plots. And what you see is that actually it seems to detect very well the first eigenfunctions. And this is true not only in 2D, but in more in 3D, for example, or in higher dimensions. The valley, they are not lines anymore. They are surfaces in 3D, or they are hypersurface of codimension 1 in any dimension in 3D. So here you have the cut, you have the trace of these surfaces. And so this network of surfaces creates a foam. And the cells are supposed to be the localization regions. So these are simulations that have been carried out by Doug Arnold at the University of Minnesota. And you see the 3-dimensional foam. And here you see some eigenfunctions, localized eigenfunctions. And you see that they sit well within the small cells of this 3-dimensional foam, which are the valley lines of the landscape. But actually, the real, it's the way we see the best, the property of the landscape and how it really predicts things that are important for the localization is by creating a conjugation operation with the Hamiltonian. Conjugation is that you're going to sort of multiply by U and divide by U on both sides of the Hamiltonian. If you do that for when U is the solution to HU equals 1, then this operator can be rewritten as such, which means that if you take the quantum states and you write it as the product of the landscape times a reduced eigenfunction, then this reduced eigenfunction is the solution of this Schrödinger-like equation, where V has disappeared, and there is a new potential that seems to appear, or a potential-like function, and this potential-like function is 1 over u. So it seems that 1 over u, that we're going to call W from now on, V, W, looks like an effective potential. And then if we think of W like as an effective potential, then it makes sense. It gives a different meaning to the valleys that we were looking at in the previous slides. Why? Because the valley of U are now the crest lines of W. They are the barrier. So the confinement here is not explained as between the valley of the landscape, but between the barriers of the effective potential, which is the reciprocal to the landscape. And not only that, but you can also prove that for any states, any quantum state, not only the eigenfunctions of H, the average of H for any quantum state, which can be usually written as the sum of the kinetic plus the potential energy, can be rewritten as the sum of something that can be interpreted as a reduced kinetic energy and something that can be interpreted as an effective potential energy. So this effective potential energy, which is the energy that the state has in the potential 1 over u, then it can be used to get some prediction on the spatial and spectral properties of the localized eigenfunctions. The first thing that can be done is to understand what is this landscape, in fact. If you make a linear decomposition of the landscape on the eigenmodes basis, so you make a linear decomposition, and these are the coefficients of the decomposition. The coefficient of the decomposition, they can be computed just by applying H and saying that HU equals 1, or applying H on the other side, are saying that H phi I equals EI phi I. And then you get from that this coefficient of the decomposition is simply the scalar product of phi I with 1 divided by EI. And from that, when you are at a given location anywhere in this domain, to understand the value of U, what this decomposition tells you is that, in fact, almost always one eigenfunction only will contribute essentially to the value of U. Why is that so? These are the eigenfunctions of H. So in these eigenfunctions, you have localized eigenfunctions. So if you have localized eigenfunctions that look like bumps, which I called local fundamental, then either X is located in the localization region of phi I, or is located outside the localization region of phi I. If X is located outside the localization region of phi I, this is almost 0. So phi I doesn't contribute to this sum. If X is located in the localization region of phi I, then this contribute. But in the localization regions, you're going to have one mode that's going to look like, quote, a fundamental, which means a bump, and all others, they will have like positive and negative part. They will be like excited eigenfunctions. So they will have something here, a scalar product, a projection on one, which will be very small. Plus, they will be higher in energy. So very quickly, only the fundamental here, sort of, the local fundamental contributes. These quantities become very small as soon as you get to excited states. So that's one way of understanding U, the landscape. You can see this field of bumps as a field of the local fundamental. Each bumps or each small sets of bumps are each corresponds to each to a localization regions, and they show you basically how the fundamental looks in this localization region. Once you have that in mind, you have that, in fact, you can predict the fundamental energy and quantum state inside each localization region, because with the landscape, you have pinpointed with the barrier of the landscape the localization regions. You know that inside each localization region, the local fundamental will look like you. And this, for example, is a 1D example where we have in green the localization landscape. And here you have 4 eigenstates. You see that they are, each of these eigenstates looks like a bump of the landscape. So that means that if each of the fundamental in each localization region sort of will look like you normalized by its norm within the localization region. If you use this approximation and you use it in this exact formula, you immediately realize that psi over u is almost constant for the local fundamental, which means that this reduced energy, kinetic energy, almost vanishes for the local fundamental. The only thing that is left, okay, sorry, shouldn't be V, this should be 1 over U, W. Okay, the only thing that is left is the W, the effective energy. So if you compute this effective energy, that will be replacing psi by U, you get this approximated formula, which is the integral of U over the integral of U squared. And also, to assume that U has a shape of a bump, of a parabolic bump, you have an even simpler formula, which tells you that the local energy of the local fundamental will be something that is 1 plus d over 4, where d is the dimension, times the minimum of W in the region. This seems to be a very crude formula, but it has been tested on many different types of potential in 1D, 2D, for uniform or Bernoulli potential, for correlated potential. And this is an example. These are simulations where you see the first eigenvalue here is in blue, the 10th eigenvalue is in yellow, the 25th eigenvalue is in green. Each of these points correspond to a different realization. Each time you take a domain, and each time you take a different realization of the disorder for a given type of disorder. Here, typically, it's going to be a uniform Anderson disorder, a checkboard on a checkboard. Each point corresponds to a different realization. Each time you have a very different eigenvalue. Each time it corresponds very precisely to the value of the minimum of the effective potential in the localization regions. And this, you have the factor here, 1.25 in dimension 1. And if we are in dimension 2, it's 1.5. So these are an example with a more complicated potential in 2D, something that looks much more like a speckled potential that can be found in a cold atom system, in an 80 by 80, much larger system. The effective potential has this very complicated shape. These are the energy, the first 300 energies computed exactly by solving the Schrödinger equation. These are the first 250 values of the minimum of the localization regions, the minimum of the effective potential in the localization regions in each of these basins. And you look the ratio of E over W mean, it's almost equal to 1.5 for the first 150 eigenfunctions. So this is a remarkable coincidence. There is something that we can compute analytically, and which shows what's going on, is when you take the simple 1D quantum well of width A, the eigenfunctions are known, they are the psi n, the energy are known, they are proportional to n plus 1 square, and the fundamental is psi square over a square. I've removed the h bar square over 2m, assumed to be equal to 1. So when you compute the SOAL localization landscape, since there is no potential, potential is 0 here, what we have to solve is minus Laplace equals 1 in 2D with the Dirichlet boundary condition on both sides of the well. The solution is a parabola, which vanishes on both sides of the well. And the inverse of this solution, the reciprocal of this solution, is the effective potential, W, which looks like this. Now, we can use this W to compute an estimate of the fundamental eigenfunctions. I said integral of u over integral of u square. Here is u, here is u square. If you compute that exactly, you get 10 over a squared to be compared to pi squared over a squared. So you get 10 to pi squared. And in fact, this 10, you look at the minimum value of the effective potential here. What is it? It's obtained at the center of the well when x equals a over 2. It's 8 over a squared. It's exactly 1.25 times 8 over a squared gives 10 over a squared. So we have exactly that. And once again, here, this is a mistake. This should be W. So if we take again our reduced formula where you have the reduced kinetic energy and the 1 over u energy here, the effective potential, and we take the ratio of this quantity, this effective potential energy over the total energy for the fundamental, for the first eigenfunction, what we obtain is that it's more than 96%, which means that the energy of the fundamental in the quantum well, which is normally 0 potential energy, full kinetic energy, in this picture of the effective potential is now almost the opposite, almost 0 kinetic energy, full potential energy. It means that this effective potential has transformed the quantum energy into some kind of classical interpretation. It's as if the energy of the system here would be the energy of a classical object, but not a point-like object. A point-like object would be sitting at the minimum of the potential and would have energy 8 over a squared. This is an extended classical object of distribution of masses psi 0 square, psi naught square. So it's lying here on the potential at rest. And the energy that it has is almost fully the energy of almost exactly the energy of the quantum wave in the quantum well. So it gives a classical picture to that. If you look at so this is for the fundamental, the first order mode. This is the second mode, the third mode, the fourth mode. And here, 100% for the fundamental, almost 100% of the fundamental, it can be interpreted through this potential energy. But the potential energy takes only 30% of the total energy of the second mode and 15%, less than 20% of the third mode, which means that there is a part of the quantum energy in this confined well that can be interpreted as a classical energy in a potential. And there is a part that comes from the fact that the wave oscillates for these quantum numbers, for these quantum states. And this is a truly kinetic energy that cannot be reduced to a classical picture. Okay, so this is about the energy. Now, let's take an example of a disorder potential to show that the landscape, it looks, a classical mistake would be to think that the landscape, it looks like solving a linear equation, HU equals 1. It looks like it's a linear problem. But there is no linear relation between the landscape or the effective potential and the initial potential. To show you that, take a 1D potential, disorder potential like this. with the amplitude of the potential that goes between 0 and 4 on 256 interval, uniformly. You solve the effective potential for that, you get something which is complicated like this. The prediction of the effective potential is that the low energy modes, they will be detected just by looking at the minima of this effective potential. So we look at the minima of this effective potential, so we rank them by order, increasing order. We draw here something that looks like a half width of the well, of the effective well that is plotted by the, that is predicted by the effective potential. And we compare it to the first 4 eigenfunctions. And these first 4 eigenfunctions sits exactly in these effective wells in the right order. Now, what we do is we take exactly the same potential with just a little detail. Now, instead going from 0 to 4, we go from 0 to 256. We have multiplied by 64 the amplitude of the potential. So what will be your prediction of where the low energy eigenfunctions sit? Guess what? Not at all at the same place, because the effective potential that is computed from this potential has nothing to do with the effective potential that is computed from that that potential. And the eigenfunctions here are predicted to be at very different places. This has nothing to do with this. And this prediction is confirmed by the computation, is exactly confirmed with the right order by the computation of the exact quantum state. So it looks linear, it's not linear. The relation between the potential and the effective potential is not linear at all. You can do that also in 2D, much more complicated. You look at, this is a binary potential made of zeros and ones. You look at you compute the effective potential plotted here in false color. You look at the basins, the deepest basins of the effective potential. Here is the deepest, here is the second deepest, the third deepest, and so on. You even draw, one can even draw lines around them at twice the value. So to draw something that would be effective wells, and we compare with the actual computation of the actual eigenfunctions. Again, it's an exact match. So far, not only we have seen that the landscape can predict the localization of the localized eigenfunctions, but also contains spectral information because it can predict the minima of the effective potential in this basin are very good predictor of the energy of the local fundamentals. But we also, outside of their localization regions, the decay, the exponential decay can be predicted by the landscape. And for that, we have to invoke something that is called the Hagman distance. The potential V in the whole domain can be used to build a metric. So you take at energy E, you take the function V minus E, you take the positive part and you square root of this. And this quantity is a metric that you can be used to determine a path. And you can compute the distance between any 2 points in the domain by just taking the infimum, taking the geodesics, using this matrix from one point to another. It has been shown that the decay of eigenfunctions, this is a work of Hagman, that you can control the decay of eigenfunctions by this distance. And this, in fact, this theory, this proof is very akin to what we in physics know very usually as the tunneling effect, or the the exponential decay through a barrier. So this quantity, if it's in 1D, looks like the exponential decay. And this in 1D, this is almost exactly the WKB theory. The only problem is that this quantity, especially, for example, if you have a potential that is disordered or a potential that is a Bernoulli potential with lots of zeros and zeros that percolate, this distance will be degenerate in many cases, which means that it will not indicate anything. You will just have a control by something. The distance will be very close to zero between any 2 points in your domain. And this will be a control by nothing, by one, not a control of the exponential decay. The idea that we have introduced is to replace here the V by the effective potential, which is a much more regular potential, which has much more structural well basins and barriers, and that shows exactly where the eigenfunctions are localized and where they decay. If you do that, if you make this leap of faith and replace V by W, in fact, you can construct a new Egmont distance. You can prove by the same technique, and I will show same type of technique. It's a bit more refined, but you can show that the decay is controlled by these eigenfunctions. And this is, for example, a logarithmic scale. The eigenfunctions number 0 fundamental first order excited mode, third excited mode for 1D potential, and this is plotted in logarithmic scale. And here in continuous line, you have the exact calculation. In dotted lines, you have the prediction by the Egmont distance of the decay. And here, this is this image that you have seen is one mode plotted in linear scale, one mode plotted, and the same mode plotted in logarithmic scale. And you can see that it decays each time, exponentially each time it crosses in region a barrier of the effective potential. So this is the same, the thing that I told you in Bernoulli, a potential with zeros and one. This is the fundamental, and this is the where you see that the fundamental here is confined within the barrier of the effective potential, and that the decay, at the logarithmic scale occurs through this barrier. To make it even more obvious, we plot here only the log of gradient psi over psi, which means it pinpoints where it highlights where the exponential decay occurs. And you see that this quantity is very large, exactly on the barrier of the effective potential. So now that we have for a local fundamental, we know that inside the localization region, it looks like U, and outside the localization region, it looks like the exponential of minus the Egmont distance based on U. We can reconstruct, and these are reconstruction from the landscape only of the of one fundamental mode at the logarithmic scale, and you can see that you have a very similar pictures. This is to say that maybe it's not a technique to really compute the quantum state. Maybe in some cases it's better to solve the Schrödinger equation. But a lot of information is stored there, and this information can be used, either theoretically or numerically to compute many things or to predict many things about this disordered system. This is the actual mathematical paper. So this is put in a way that may well be more appealing to mathematicians and maybe less appealing to physicists. Here is the control inequality. And basically what it says is that if you are in a domain here and you look at where the potential is larger than the angle value, in fact, you take a delta to have some kind of small security, some safety. So over delta, you have wells here that are basically the basins where W will be smaller than lambda. And if you take any points, you take any points in the domain, you look at this distance to the closest well, distance understood in terms of Egmont distance, and this will give you the exponential control on the eigenfunctions, and use through this control the fact that you can exponentially separate the wells. It gives you an almost diagonalization of the Hamiltonian to an exponentially close diagonalization of the Hamiltonian, which means that any function, in fact, any function of the eigenfunction of the whole system can be understood as can be shown to be close to one or several eigenfunctions around in the same range, in the same eigenvalue range of the wells, and conversely, which means that if two wells are distant or have eigenvalues that are very different, it means that you have almost localization, exponential localization only in one of these wells. And not only that, but also it gives you some kind of control on the density of state. So this is the philosophy of this. So we have seen now that we have spatial prediction and spatial understanding how the states are localized, how they decay outside their wells. We can predict the density of states, or more precisely, the integrated density of state, the counting functions. So usually, they are in two ways actually. The first way is to use the asymptotic Weiss formula. Asymptotic Weiss formula tells you that due to the uncertainty principle of quantum waves, delta x, delta k is of the order one, counting eigenvalue below a certain eigenvalue amounts to simply counting volume in phase space. It means that if you want to count how many eigenvalues are smaller than E, you simply count how many ones you can store in the space where h of xk, which is the classical expression for h, for the Hamiltonian, where this is smaller than E. So this is Weil's asymptotic law. The counting function at energy E is essentially asymptotically given by this volume with a prefactor. This is, of course, this is an asymptotic law that is valid only at higher energy. So but it fails for disordered potential, intermediate or low energy. And especially at very low energy in disordered potential, you have a dramatic loss of eigenfunctions, which are called Lifshitz tails. And these are not predicted at all by this type of approximation. What the conjectured law that we have proposed is to replace here the V that enters the H by W and use this effective potential that gives more classical understanding of the shape of the eigenfunctions to use it to predict an integrated density of state. When we do so, these are numerical simulations for uniform Anderson potential, Boolean, which means binary disorder, zeros and ones, correlated potentials, even periodic potential. In each case, the Weil asymptotic formula is given in green. The exact counting function is given in black. It's this discontinuous, step-like curve. The prediction with W is in red. So you see, it has nothing to do with disorder here. It's clear, because even for the periodic potential, we are almost sitting over the prediction. This is something, it works for disordered potential, but it works also for non-disordered potential. It's a universal machinery. There is something at work here that the wave sees this effective potential. Okay, this is the first way. This is the first way we can predict the integrated density of state. We have introduced recently a second way of predicting the integrated density of state, the counting function, which is called the landscape law. The landscape law is to, the philosophy is to use the fact that the minima at very low, at the very low end of the spectrum, it seems that the minima, they are very good predictors of the energy. But in fact, the minima can be used not only at the very low end of the spectrum, but everywhere. And we can construct everywhere in the spectrum. We can construct an approximation to the counting function of the Hamiltonian by computing this formula. This formula says if you are at an eigenvalue lambda or an energy, which is the energy to us, what you do is you divide your domain, you partition your domain in cubes of side lengths 1/square root of lambda. So you take your domain, you cut it like this. And then you're going to look in each of these cubes called Q. In each of these cubes, you're going to count how many of them are cubes where the minimum over the cubes of W is smaller or equal to lambda. So the size of 1/square root of lambda is the natural size that comes from the scaling of the Laplacian. It's what it takes to host a localized. So this size is what it takes to host a localized eigenfunctions of energy lambda. So you count the number of such cubes, and this gives you a counting. It has been proved recently. This is a theorem, this is not an approximation, that you can actually bound the actual bounding functions from above and below on the entire spectrum by using NU with just a multiplicative shift in the eigenfunction, in the eigenvalue. Which means that, and to our knowledge, this is the first non-asymptotic estimate of the density of state on the entire spectrum. So this tells you that basically, if you plot NU in logarithmic scale, you enclose it in a tube. You can enclose n of lambda in a tube where you have NU below and NU above. That NU follows the shape very closely of the counting functions, and not only asymptotically at infinity or around zero, everywhere. The constants do not depend on lambda. They do not depend on the amplitude of infinity, of the potential. They depend on the average value of the potential. It applies to any potential. And it seems to be a result that is better than any other result that was prior to that in this area. So, for example, this result allows us to estimate on the shape of the decay of the Lifshitz tail in the case of the Anderson uniform and Anderson binary potential, or even in the case of potential that are distributed with a very small tail near zero, which gives rise to what is called pasture tail. And we get something that is better than the previous known result. In short, we take a log out of that. So we have exponentially better result. We don't have to go to the log of n to have the estimate. And we have estimate directly on the log of the counting functions. So these are numerical simulations. For example, a 1D type binding Hamiltonian with 100,000 sites, a Bernoulli potential where the potential is either 0 or 1. This is the counting function, N of E, on all the energy spectrum, and with the very large dynamic. This is N of U. So theorem says that you can enclose this between this and that by just shifting this by here in logarithmic scale. That will be a translation, vertical and horizontal translation. In fact, you can, but it's even better than that. You can almost superimpose it, with a right choice of the parameter. It seems that you have an almost exact predictor of the counting function. This is the same type of simulations for not for binary, but for a uniform potential. And you have also the same type of result. Here you see the tube that the prediction by the theorem, but in fact they can almost be superimposed. So so far everything that just to summarize quickly, we have shown that there are lots of spectral and spatial information within this function landscape that can be extracted. These are results that have been published or which are on archive. What I'm going to speak very quickly about things that are work in progress. But so it's despite the fact that it's a school, just to show you that we can use the landscape in the framework of the cold atoms. And the thing that we are working on, one of the things that we are working on right now, is the prediction of the spectral function. Dominique told you a bit about that. So spectral function. So if you have a state psi, and you want to measure the energy on a state psi, you know that the energy that you're going to measure by a quantum measurement will follow a probability density function that is given by its projection on the eigen function of the Hamiltonian with the delta of E minus En. And if the state is a plane wave of wave vector 0, simply what you obtain is the spectral function at k equals 0, which is this formula. So the idea is, the question is, can we say something? Can we make any prediction on the spectral function in a disordered potential, typically a spectral potential of cold atoms, using the landscape? And the first idea is, okay, we can do maybe we can do things. And the first idea is to use exactly the same approach that was used for the W-based Weil's law. You know, the Weil's formula, correct, rewritten in the W framework, is to work in phase space. Work in phase space, and or sort of, it's a generalization of what has been done for the Weil's formula. To compute in phase space, you have to have a distribution of in phase space of the eigenfunction, an equivalent of the eigenfunction in phase space, and that is called the Wigner function. The Wigner function takes a quantum state and gives you a distribution in phase space. Okay, it has almost the property of the probability distribution. It's not always positive, but it has very nice properties that I won't discuss here because I don't have time. But you can, for the sake of understanding so far, you can imagine that it gives you sort of the distribution of the wave function in phase space. And there is analogous for the operator, which is called the Weil's transform, which transform an operator A into a function in phase space xk. And the very important property is that when you do that, for any quantum state psi, and for any observable A, the average of the observable of the state psi is given by the integral of the Wigner function times the Weil's transform integrated over all phase space. So really, it works like if you had some kind of classical object in phase space. So you use this, you take that, and the second idea is to say, okay, what is the energy distribution of a state? The energy distribution of the state, you can find it, you know, by saying, okay, the average energy of a state psi is given by this. It's also given by this formula because of what I just showed you. And you can say, okay, I can reinterpret that as an integral over phase space where I regroup everything here by constant value of the energy. When I do that, this quantity looks very much, you know, when you slice your phase space by value of the energy between E and E plus DE. When you do that, this looks very much like a PDF of E. And of course, the conjecture that we use is that we don't want to use V because V is a very poor object. We know that it's disorder. We're going to use W as we did for Weil's law because it shapes the phase space in a much nicer way. So we use, instead of V here, we use W. And we use the Weil's transform, so we use the Weil's transform of the operator with W. And when we do that, we take that for a spectral potential, which has an exponential distribution of value of the potential and a Gaussian correlation. I'm not sure that Dominique talked about that, but you use a dimensionless parameter eta, which tells you that when eta is smaller than 1, we are what Dominique called the quantum regime. And here, when eta is much larger than 1, we reach the semi-classical regime. So it gives, it sort of measure the potential with respect to the typical correlation distance. When you do that and you compute the spectral function here for in such a system, this is the typical estimate of the spectral function that you can compute by a state-of-the-art estimate, like in this paper. This is the estimate obtained by the landscape, the prediction by the landscape, and this is the difference between the estimate. This is the correction. This is for eta equals 20, which means very semi-classical regime, very classical, you know, high in the deep in the semi-classical regime. But now, if you do that for many different values of eta, from eta equals 20, but now down to eta equals 0.1, that means it's very deep in the quantum regime. What we see is that the prediction of the landscape follows the evolution of the spectral function, which is almost exponential, very deep, because it's a distribution of the potential here in the classical limit. But this is something that is very different. Not only that, but the sort of the difference also looks like to have some kind of, I wouldn't say universal, but general shape, the same shape, you know, like there is a general correction error that could be found. And so this is very promising, you know. That's it seems that not only we reach something that looks like a general way of predicting the spectral function, but also we have leads to have a general correction as if this first prediction, the way I showed you, were the first order term of a general expansion. Okay, I think it's for me time to wrap up. I will first say that okay, we are not the only one. If you want to know more the localization landscape, you will find on the web in our work. But there are also other teams working on the landscape these days, and especially many exciting results here on Dirac fermions. So it seems that it's a spreading. And just to conclude, and is that the localization landscape, in fact, the take-home message is, okay, we solve a linear problem, one single linear problem, which is of course much easier, but solving this problem gives a lot of information. It gives the localization some regions, it gives the shape of the fundamental eigenfunction in each of this region, it gives its energy. Actually, the reciprocal of the landscape can be understood as an effective confining potential. Outside of the confining regions, it gives the range decay of the states. And also it provides two ways to compute, to assess the density of states. We have not yet understood well what are the pros and cons of both, but there is something that is obvious, is that, for example, the landscape law is something that works on the bound from above and below on the entire spectrum. And so in the cold atom problem that is of interest to us, we are computing the spectral functions. I've shown you in simulation in 1D. We are doing it also in 2D. We hope to do that in 3D and to have a general framework to compute not only the first order, but also the correction. Okay, thank you for your attention.
Thanks, Marcel. Questions? Maybe Dominique, you had one at some point? All right.
I would like to ask a question, but I'm sorry I cannot raise a hand because I think I'm kind of co-organizer for some reason. I don't have the hand.
But that's fine. You can go on.
Yes, so I have a question about the first part of your talk. So you have shown that using this landscape approach, you can get a lot of information about low energy localized states. But does it break down at some point if you go higher in energy? Something doesn't work anymore?
So it depends of what you mean by work. So if working means predicting the energy that are predicted, the single values of energy that are predicted are the localization landscape shows you the basins of localization. In each of these basins, the minimum will give you an approximation of the a very good estimate of the energy of the localized eigenfunction in this basin. Now, if you go to higher order mode, then what do you expect? What are the questions? The first question that you can ask is maybe not exact the value of the. You can ask either the value of the first excited state in this localization region, or simply what are the number of states around a given energy. For that, you have the density of states. So the density of states, there is also, and the density of states, it doesn't break up because I've showed you the landscape law. It doesn't break. It shows you something that connects from 0 to infinity. Now, if you want to ask specific question of what is the energy of the second state in a given localization region, then there are estimates that you can build from the landscape. Because, but this estimate, it comes from the fact that the bottom. It's like you are in you can have each basin looks very much like a classical basin, and it's almost like an harmonic oscillator locally. So you can use the fact that the curvature of the localization landscape of the effective potential at the bottom, and use this curvature to predict not only the fundamental, but at least the second or the third. Of course, the quality of the exact prediction in each well will decrease as you go higher. But then what takes charge of the question of what is the energy is the density of states then. And then we have estimates also. I don't know, I'm not sure I'm answering the question, but
yeah, Marcel, can I go on with this question of Sergey?
Yes,
is there any hope to be able to calculate the localized states around the mobility edge? You're not surprised by the question?
No, I'm not surprised I'm not surprised at all. I'm not surprised at all.
No, but it seems that it is a legitimate or natural extension of the question of Sergey. So
yes, I understand. I think that we had to add another ingredient to that because as first, to detect the mobility edge, as Dominique said, we cannot expect to do that on a single particle expression such as the density of state. So we're going to have to look to more complicated quantities, to transport quantities, and this we didn't have done yet. The second thing is that I'm not sure everything that I've shown so far about the spatial information, the spatial structure, is very related to the lower end of the spectrum.
It is true.
To go to higher energies, I think you have to look at something that is not only the spatial structure of the landscape in real space, but also the structure of the landscape in the reciprocal space, in the K-space. And that is something that we are investigating.
Okay.
And I think that you won't find, you know, the structure of the eigenfunctions at the mobility edge. They are, you know, they're going to be multifractal. They're going to be very complicated. They won't obey something like it's the fundamental mode of a single parabolic basin. They won't look like this. So we have to add another ingredient, and I think we have at least hopes to know what ingredient we have to add. But this is not in what I presented here.
Okay, thank you.
Other questions? Yeah, I have one on the, maybe Giuliano then.
I would like also to ask a question. But
Okay, go ahead. Giuliano was first, so. Giuliano, put your microphone on.
Yes. Okay, sorry. So my question is, how do you compute numerically this landscape function U? From the numerical point of view, you use what is you search 0 in a multidimensional space, like.
No, it's U is that's the catch. U is very simple to compute. It's HU equals 1.
But numeric HU equal to 1 is what you are searching a 0 of a function, right?
No, you just basically you are solving a linear problem. You discretize by the way you want, the best discretization scheme that you want, and you are basically solving. You know, H psi equal E psi is a difficult problem to solve because you have an infinite number of eigenfunctions and eigenvalues, and you have to stop somewhere. Plus, it's not a linear problem as in terms of resolution, but H equals 1 is a purely linear problem. You have H as the matrix and 1 as the vector, and you solve AX equal B. It's as simple as that. That's the beauty of the interest of the method, is that it's so simple to get the landscape. It's not difficult to get the landscape.
Okay. Okay, thank you.
So I have a question. So for example, if we look at your landscape that you show here on the slide, that you have two minima which are close to each other, you would expect states to hybridize. So then that
absolutely.
So do you get that from this kind of approach?
If you look at if you simply look at the minima, actually, if you have two wells, it's the way you compute. So I didn't go into the details. This is a work that has been done by a student, Perceval Desforges. What I showed here, it's a very simple approach where you simply draw the valley, all the valleys, and in an indistinguished manner. Okay, you have to be a bit more careful than that. Just drawing the valley won't give you the real localization regions, because you can exactly have the type of things that you mentioned. Yeah, you might have some kind of, two regions that are close to each other like this. And in fact, there is a very small ripple in between, and there is a minimum here. There is a minimum here.
It seems that one
there.
of the values, Marcel, it seems that one of the values that you showed is exactly like that. It's across two zones.
Okay.
It seems that I have seen that.
So actually, in fact, it's a difference in between what is topography and what is eigenfunctions. Topography will tell you there you have a basin. but this basin might not be eligible to host an eigenfunction. So there is another additional work, which is an algorithmic work, to say whether the valleys or the barrier are actually admissible to create localization regions, you know. So if you want to say this is a localization regions, this is a cell, you have to say, okay, is the valley large enough? So, and this, to help you, you have this 1 + d/4 criterion, which tells you, is the basin deep enough? If the basin is not deep enough, you say this is not a true basin. The real basin is larger than that.
But
So
Marcel, can you show the next transparencies? Because I think that no, too far back.
This I think you refer to this one. This one
yes,
here.
Next one. No, or before. But there was one where clearly there was one localized function. Yeah, here. Yeah, look, mod 5. Mod 5 is clearly.
Yeah. Mod 5 is this.
Yeah.
And
mod
this
5,
line. And actually, this line is already open. It's already open. So this is what you call the hybridized mode. And I expect the first excited state in this localization region to be like positive here and negative there. That's exactly that. But then but this happens only if you want to if you are interested in really saying this is a region, if you want to detect the regions, because all the techniques that I showed after, you know, the computing of the density of state or the computing of the energies, because if you compute the energy, what you're gonna have from this? You're gonna have a minimum of here, a minimum there. So it will give you two minima that very close to each other. And that will be exactly the situation that you will get. You will have actually two values of the energy very close to each other. So it's only if you want to interpret this as localization regions or not that you have to be careful. But the averaging technique for computing the density of state, they won't be disturbed by that.
No, but let me follow on that remark of Jacqueline, because let's suppose you have an hybridization between two functions which have a slightly different energies. Yes. Then we can begin to think about oscillations and dynamics and
absolutely.
Stuff like that.
Okay, that's
so I think her equation points towards maybe these kind of things.
Yeah, and it's also, I wonder whether, I mean, when you talk about experiments, you can have two approaches. One is to consider a disordered potential and see how it modifies transport, localization, and whatever. I was wondering if you want to do the other way. So you make an experiment and you want to try to study the disorder. Can this approach give you more information on the disorder than other? I mean,
absolutely. Okay, maybe that would be that. I would have to show you. Maybe I'm going to show you after, because the time is scarce. But
yeah, and we have to meet one day.
and I didn't show, but we have done. Actually, we have collaborated with people doing experiments with mechanical systems, for example, where they had like a mechanical system. They didn't know what was inside. And by simply measuring, we could say, okay, this is the type of where we could not only predict the localization region and the frequency of the first vibrations, but we could just blindly, you know, just by making a static measurement. So we don't need to make a steady state vibration measurement to predict the vibration property. And we have done also, not only we have done that, but we have done even the other way around, is to use the localization landscape in this type of system as a design tool, saying we want this type of property of vibration, what should be, and just by optimizing the landscape in this object, we have obtained the localization property that we wanted.
Okay. Yeah.
Okay, I think we have to move on, otherwise we will have no time later. Jacqueline?
Okay.
Okay. So can we make a short break?
Maybe we still take 5-minute break, and and we reconvene in like 5 minutes or so for Sergey's talk.